Good morning. I'm Rajitha, working as Assistant Professor of Artificial Intelligence and Data Science Department in SNS College of Engineering. Topic is inferential statistics. Let's move on to the subtopic one tail and two tail test in hypothesis testing. What is hypothesis testing? Hypothesis testing is a fundamental statistical technique used to make decision or inference about population parameter based on sample data. The process begins by formulating two competing hypotheses. The first is the null hypothesis, which typically represent the current state or a neutral, such as there is no effect or no difference. The second is alternative hypothesis, which propose that there is a statistically significant effect or difference in the population. Hypothesis testing help us determine whether the observed result from a sample or due to random chance or indicative of a real effect. It involves calculating a test statistics and comparing it to critical values derived from probability distribution such as the Z or T distribution. Based on the comparison, we either reject the null hypothesis or fail to reject it. The significance level, usually set at 5%, is the threshold for making this decision. If the p value is less than alpha, the result is considered statistically significant, leading to rejection of the null hypothesis. Next, one-tail test. A one-tail test, also called a directional test, is used when the alternative hypothesis predict a specific direction of the effect. This means we are only interested in determining whether the sample statistic is either significantly greater than or significantly less than the hypothesized population value, but not both. For instance, we want to test whether the average score of students is greater than 70. We use we use a right tail test. In this case, the alternative hypothesis is H1 mu greater than 70. If we suspect that the machine is underfilling bottles and want to check if the mean fill is less than 500 ml, we use a left tail test with H1 mu less than 500. The entire significance level is allocated to one side of the distribution. This approach increases the power of the test to detect an effect in the specified direction, but it cannot detect effects in the opposite direction. The one tail test is appropriate only when there is a strong theoretical to expect the effect to go in one direction. And the two-tailed test is in contrast to the one-tailed test. A two-tailed test is non-directional and is used when we are interested in deducting any significant difference from the hypothesized values regardless of direction. The alternative hypothesis in this case is h1 mu is not equal to x, where x is the value being tested. This test check whether the observed sample mean is significantly higher or lower than the population mean. For example, suppose a manufacturer claim a battery lost 12 hours on average, and we want to test whether it differs from that. We use a two-tailed test. In this test, the total significance level is split evenly between the two tail of the distribution. A test statistics that falls in either tail beyond the critical values leads to rejection of the null hypothesis. This method is more conservative and should be used when there is no prior reason to assume a particular direction of the effect. It ensures that deviation on both side of the mean are taken into account. In the situation and usages, deciding between one tail and two tail test is crucial in hypothesis testing. The choice depends on the nature of the research question and the hypothesis being tested. If the research question specify a direction such as testing whether a new drug is more effective or whether machine performance has improved, a one tail test is appropriate. This test will only detect an effect in that specified direction. However, if the hypothesis does not specify a direction or if we are equally interested in change in both direction, then a two-tailed test is more suitable. For example, if we want to determine whether a new method changes the average outcome in any direction, increase or decrease, we must use a two-tailed test using a one-tailed test. In such case, increase the risk of overlooking significant effect in the unintended direction. Therefore, while one-tailed tests offer more statistical power for directional testing, two-tailed tests are more balanced and cautious when direction is uncertain. In a real-time example, make the concept of one-tail and two-tail test for more relatable. In one-tail test scenario, consider a student who claim their test score is consistently above 70 percentage. To verify this, we perform a right tail test. In manufacturing, if a soft drink company suspect that bottles are underfilled and want to test, um, if the mean volume is less than 500 ml, a left tail test is appropriate. Similarly, a tech company may claim its battery lost more than 8 hours. Another case for a right tail test. A weight loss product promising more than 5 kg reduction or a delivery service promising to deliver in under 30 minutes or further example of one-tailed hypothesis. In two-tailed test situation, suppose we are testing whether a new teaching method changes students' score without specifying the direction of change. We are interested in any change, whether better or worse. First, therefore, both tails of the distribution must be considered. Two-tailed tests are common in academic, medical, and industrial research where both increases and decreases are equally important. One worked example given. Let's go through a worked example of a one-tailed test. Suppose the current average test score for a subject is 70, and we want to test whether a new teaching method improve this score. The null hypothesis is H naught mu equal to 70 and the alternative hypothesis is H1, that is mu greater than 70. We collect a sample of 30 students who were taught using the new method. Suppose the new sample mean is 73 and the sample standard deviation is 5. We calculate the test statistic using the formula for one sample t test, that is t equal to x bar minus mu divided by s divided by root of n bar. X bar is the sample mean, mu is the population mean, s is the standard deviation and n is the sample size. Substituting values, we get t equal to 73 minus 70 divided by 5 by root of 30. We compute the t value and compare it with the critical t value of alpha. Critical value of 29 degree of freedom at alpha is 0.05. Right tail. If the computed t is greater, the critical T. We reject H naught. This shows the new method significantly improves score. Otherwise, we conclude the difference is not statistically difference. And the summary is one tailed is rejection on one side, two tailed is rejection on both sides. Table comparing hypothesis, critical region, and use cases. Visual representation of one tailed and two tailed test are helpful for quick understanding. In a one-tailed test, the rejection region is concentrated in one tail of the distribution, either left or right. This area corresponds to the significance level, usually 5%. If the test statistics falls into this shaded region, the null hypothesis is rejected. In a two-tailed test, uh, the rejection region is split into two tails, each having half of the total alpha. For example, 2.5 percentage on each side if alpha equal to 0.05. The middle portion of the graph represent the region where we fail to reject the null hypothesis. These visuals are often represented as bell-shaped curve with critical value and shaded rejection zones clearly marked. Visual aids help in interpreting statistical result and making informed decision. They are especially useful for students and practitioner who are more comfortable with visual information than numerical calculation. Thank you.